Thank you for joining again. I was just looking at some of the chat windows. Some of the chat discussion here. I'll do a quick recap before we start session 3, just so that everybody is on the same page. And again, I forgot to do it at 1 p.m. because I thought I was running late. So I'll quickly do a quick recap and then we'll progress. Again, I was also just looking at a bunch of folks' comments, and in general, some of them also sent me one-on-one message. So what I'll do is, I think the second session was slightly faster than the first one. So some people got lost a little. So let me just redo this. Let me make a quick poll just so that should we go at okay. Compared to second session, what speed should we go? Same, faster. Again, I'm just making it up as we speak, as others join. Okay, I'm quickly posting a poll while everybody joins it. I'm just showing it on the stage. So I just wanted to get your quick point. How do we want to go as compared to the second session? The first session, everybody was super happy at the speed we were going. What about the second session? Should we go at the same speed, slower, faster? Because I got a few messages that maybe we should go a little slower. Yeah, because as we keep progressing, the concepts only will get a little more harder to digest and think through. I think in the second session, we mostly did a code walkthrough where I tried to go as slow as possible because everybody may not be comfortable. Okay, I'll wait for everybody to participate in the poll. In the meantime, let me tackle a few questions. So will we get notes for this? Yes. So we have, I think, I've written a lot of detailed notes. Whatever topics we cover in today's series of sessions, we will send you the PDF, the external links, the code links, everything we'll send it to you via email using the registered email that you've shared. So we will post that. Don't worry about it. Very nice. So another request here is please give us some exercises. Very nice point. I'll point you to some of these. Very nice. So think of it this way, right? A simple exercise that I can quickly think of is this whole hypothesis testing that we've done using permutation test. Can you, for a specific type of distributions, assume that your control and treatment distributions come from a specific class of distributions? We used Pareto. Use let's say normal, use exponential, use some of these distributions and fix the size of your control and treatment, fix the sample size. Once you fix the sample size, start doing an experimentation. Again, it's a pure simulation experiment, right? Trying to see what is the false positive rate and what is the false negative rate, basically type 1 error and type 2 errors. So can you quantify that? Again, doing it in general mathematically is very hard, but it's a very nice blog post and nice simulation that you can do where you say, hey, if my control and treatment variables come from so and so distribution, and if the size of my control and treatment, which are n and m, is this, and if my number of resamplings is, let's say, 10,000, which is a fairly reasonable number, how often in permutation testing will I encounter this problem of type 1 or type 2 errors? That's a simple exercise. It's an extension of the code that we discussed. It's just that you have to repeat it multiple times and then plot and do simple data analysis on top of it. That's very, very useful. It's a phenomenally good yet very powerful blog that you can write, right? Because it's simple to explain, but that's what stats guys or even data scientists should do in terms of experimentation, right? So let's not forget that foundation. So it's a great exercise for you to take from here. Okay, so this is why do we compute p-value for m greater than equal to m observed, but not m equals to m observed? The reason is we are saying, see, we observed, let's assume a median difference of 20. What we are literally saying here is how likely, because the 20 is a real number, right? The probability of exactly observing the 20 is quite low, right? I mean, if you think of continuous random variables or real valued random variables, the probability of exactly getting the 20 is quite low, right? So we say, what is the probability of observing a value as high as 20 or higher? Okay, so it's more about a test of it's more about saying, can it be as extreme as 20 or more? 20 in this case is m observed, right? So it's more about the extremity, not about the exact value. Very nice question. So this is from Radhika, which is, can you please suggest some good books to strengthen statistics concepts? There are a bunch of very nice ones. Think Stats is a freely available book from Greenpeace publication. I really like that book. It's a simple book, very hands-on book. They don't go too deep into theory, but it's fairly hands-on. I really like that book. They take actual publicly available data and explain concepts from that. Then there is something called as Art of the Stats, I think, which is also considered a very good book. Then there is Practical Statistics for Data Scientists. I think that's the name of the title from O'Reilly, which is also a good book. But one small problem that I observe in many of these books is they go reasonably well on the applied side, but they may not have ample space on the theoretical front, on the more foundations, why and why not stuff. They explain the coding part, they explain simulations, all of that they do very well. So that's what some of these O'Reilly like books are, or even Think Stats types of books. They're very hands-on, but they lack the rigor, the theoretical rigor and the depth. For that, you can pick up a standard probability and statistics textbook from any major college courses, but they tend to be too theoretical. So the middle path that I suggest you is learn the applied aspects from these O'Reilly books or from Think Stats or some of these nice books. For the mathematical depth, I use Wikipedia often. I don't have a regular statistics textbook with me, because I typically go to Wikipedia. Wikipedia tends to be very good. Or if there is a specific topic, I go Google search for it. I get a good technical blog on Medium written by somebody who is genuine, or I go to lecture notes at universities. That gives me that rigor and depth. So there is no one single book, unfortunately. So it's a combination of these hands-on books from O'Reilly or Think Stats and some rigor from Wikipedia, or the mathematical depth from Wikipedia, a bunch of research papers or lecture notes. Okay, cool. Okay, so I'll wrap up the poll. It seems like close to 60% want it at the same speed, 26% slower, 13% faster. So I'll try to maintain the same pace. Wherever I believe that the concept is slightly tricky, I'll go a little slow, only in some places. But there will be some topics that I'll go a little fast also, just in the interest of time. Okay, cool. So again, please understand that the objective here is not to throw so many concepts down your throat. That's not the objective. Even if you learn only limited set of concepts, let's learn them thoroughly. Again, if time permits, we'll do one more session where we can cover more topics, right? This is the first of its type that we are also experimenting with. So it's better to cover only few, but do them thoroughly as best as we can. But I'll try to give you that breadth, right? I might have to skip a few topics. Let's see with this session, because I have only one more session. I'll try and, because I really, really want to cover the multi-arm bandits, some of those concepts also. We'll try and do our best in that front. Some simulations, some code and things like that. Okay, sounds good. We'll wrap up the poll now. Let me close the poll and hide it from stage. Okay, so with that, very nice. So I'll answer a couple of questions and then we'll start in a minute or so while others join in. What's the difference between a z-test and a permutation test? Very nice. So I have a slide on that actually. So there are tons of statistical tests that are available. You have t-test, z-test, F-test, ANOVA, tons of tests. Every test makes a fundamental assumption. The Z-test assumes that the data that you have is Gaussian distributed, which is not true always, right? For example, if you're looking at time spent on web pages or time spent on videos, it's often not Gaussian distributed or normally distributed. So the beauty of permutation test is it is something called as a non-parametric test, which means it is not making any assumptions of the underlying distribution of data. It is not making parametric assumptions about the distribution of data. But no test is perfect. Every test has its own limitations. We'll cover some of those. Permutation test, again, I'll compare permutation test and Mann-Whitney U. There you'll understand some of the drawbacks of permutation test and how Mann-Whitney U actually gets over those. And Mann-Whitney U is one of the most powerful statistical techniques, but it also has its own limitations. Nothing is limitation free, right? So the Z-test in practice is less used because it makes very strong assumptions about the distribution of the underlying data, while permutation testing doesn't. That's the key. Okay, somebody wants me to revisit type 1 and type 2 error. So let's do that. So I'll quickly revisit type 1, type 2, recap what we studied in the previous session and start this. Okay, let's go quickly through that. Okay, cool. So I'm assuming everything is visible and clear. Okay, just give me a second. I'll keep my phone handy in case there is any message of something not working. Okay, cool. Okay, I'll give a quick recap as somebody is suggesting. Sure. So yes. I'm just going there. First, I'll explain what a lot of students asked, which is type 1 and type 2 error. Where is that slide? Okay, we're going to the very top. Somewhere it will be here. Just give me a second. I'm also searching. Where did that go? Okay, it's here. Okay, so let's assume. Okay, so let's go step by step and understand that. Cool. So what we have here is, let's assume that H0 is actually true. When H0 is actually true, which means the null hypothesis is true, but based on our statistical test, let's assume the decision that we made is we accepted H0. Perfect. H0 is actually true and we accepted H0. So there is no problem here, right? Type 1 error is when H0 is actually true, but we accepted the alternative hypothesis. In this case, we have a false positive, also referred to as type 1 error. Again, the simplest way to remember what is type 1, what is type 2 is to just remember this diagram. This is what I often draw whenever I get confused. Okay, so type 1 sits in the bottom left corner. Okay, where if H0 is actually true, but we rejected H0 and accepted alternative hypothesis, it's called type 1 error. Similarly, type 2 error is when the alternative hypothesis is actually true, but we rejected, we simply accepted null hypothesis because of the p-value that we got. That is called as a false negative or a type 2 error. That's the idea behind it. Okay, this is exactly like confusion matrix as somebody is just pointing out, right? That's it. It's as simple as that. Okay, so okay, cool. So where did we stop last time? Okay, I think we stopped here, right? So I think, yeah. So the second session, I'll give a quick recap of the second session. In the second session, after learning the basics of permutation testing, we understood the terminology of hypothesis testing. So we have null hypothesis. In the context of the problem that we're looking at, it means that the control and treatment have similar distributions, or they're very more or less the same. The alternative hypothesis here is that the treatment and control are not the same, right? That's what is referred to as HA, or sometimes also referred to as H1. Okay, in some Wikipedia articles and research blogs, you might see it as H1 and not HA. Now, what is a test statistic? It is a numerical value that we measure. Okay, so in this case, in our case of permutation testing, the mean difference between treatment and control is what we used as a test statistic. And we computed the p-value. Now, what is p-value? P-value is nothing but what is the probability of observing the test statistic value. what is the probability of observing the test statistic value as extreme as what we empirically observed, which was MOBS. What is the probability as extreme as this, or even more than this, under the null hypothesis? And our null hypothesis was that XC is similar to XT, right? Which is same as this probability. So this probability that we computed is called the p-value. So in any hypothesis testing, first we need to know what is the null hypothesis, what is the alternative hypothesis, what is the test statistic, and then we compute p-value based on the test statistics distribution. Okay. Then we have something called as a significance level. This is to be set by the scientist or the statistician, and we reject the null hypothesis if the p-value is less than the significance level that we set. Imagine if this is set to 5%, and if the p-value that we get is 2%, we reject the null hypothesis, because under this null hypothesis, the probability of obtaining, which is nothing but the p-value, the probability of obtaining this extreme value is quite small, and hence the null hypothesis may not be likely to be true, and hence we reject the null hypothesis, and else we accept the null hypothesis. Simple. Now, okay, the same thing. So for example, imagine the p-value that we got is 2%. You always reject or accept a null hypothesis at a significance level. If what we obtained is 2%, then we say, if our significance level is 5%, because 2 is less than 5, we reject the null hypothesis at 5% significance level. But if our significance level was 1%, then we will accept null hypothesis at 1%. So for stuff where things are more critical, we make this alpha value, this significance level value, smaller, because we don't want to have errors. Okay, so these are the types of errors that we just discussed. Again, so the power, so there is also a term called power of a distribution. Power is nothing but 1 minus beta. What it means here is how often is a case where when the alternative hypothesis is actually true, we are also accepting the alternative hypothesis. How often do we do that? Or what is the probability of doing that? That's called the power of your test. Now, we also discussed why we chose the null hypothesis as the control and treatment being the same, primarily because we can simulate this behavior using a computer. While we can't simulate the infinitely many differences that you will have. Imagine if your null hypothesis is that XC is not same as XT. There are infinitely many such possibilities, and simulating all those is simply impossible. Okay, simple logic. Then we discussed about the code for permutation testing, and we discussed various scenarios. One key observation here is permutation testing may not work very well if you have very small samples, and this is very important. If you have very small samples and if the distributions are only slightly different, okay, then there is a problem. Okay, so again, if the sample size is small and if the distributions are very close, then the whole idea of permutation testing may not work as well in all situations. Then we discussed about what happens if you keep increasing k. Of course, increasing k from 100 to 1000 makes an impact, but beyond 10,000, not a significant impact in general. Then we talked about what happens if one sample is large and another sample is smaller, right? Even if one of the samples is large, the permutation test tends to work reasonably well as long as the other sample is also reasonably sized, not too small. Then we discussed about what happens in medical domain when the size of your samples of control and treatment are very small. A lot of things go wrong. That's where we'll go to Mann-Whitney U. Right? So we also said if you have small samples, what is the maximum value of k? Right? A very, very simple mathematical thought. Now we'll start the third part here. Right? In the third part, first, always remember, no statistical test is perfect. Any statistical test that you have will have limitations. It will only work in some settings. Somebody was asking this earlier. We have so many other tests. Why are we studying permutation tests so much, right? And the reason being that it is never perfect. Okay, no test is perfect.